Hi, and welcome to our discussion of atmospheric dynamics. In this video, we're going to look at the vorticity equation, and this is the first video of many that discusses the vorticity equation. So where we left off in our discussion of the mass continuity equation, we derived the kinematic method of vertical motions where we looked at the mass continuity equation and we saw that convergence or divergence results in vertical motions. Now, the problem with that, though, is that sometimes it's difficult to measure divergence in the atmosphere. We said that down low it's not too hard because you can see the wind flowing into lows and out of highs, so there's lots of convergence and divergence as a result of frictional effects. In the upper atmosphere, though, it's really hard to measure because in the jet stream, the winds are moving along pretty well, and it's hard to see that convergence or divergence. However, in the middle of the atmosphere, there's really no convergence or divergence at all. Typically, these two terms of the divergence equation, the speed is offset by direction, meaning that if you have speed convergence as the isobars come, or as the wind speeds slow down, you have the isobars or the contours spreading out where you have directional divergence. Remember in the last video we said that directional divergence is also called diffluence. So, our measurement systems are not exact, they're not precise, there are some errors. The way we measure winds in the upper atmosphere is using radiosondes. We send up balloons, and balloons do have some errors in their measurements of wind. So if you have some errors, then the calculation of divergence is going to be an error. Typically, you're looking at speed and direction offsetting each other. These are two big numbers. You take the difference between two big numbers, you get a small one, and you're not sure if it's plus or negative. So that's a problem with measuring divergence in the upper atmosphere. So we got to figure out another way. Divergence is really not going to tell us if there's rising and sinking motions in the atmosphere. We got to find another method that helps us figure out where the air is going up and where the air is coming down. So back in the 1940s, late 40s and early 50s, research meteorologists found that vorticity was a good method for figuring out where there is divergence. There's a relationship between vorticity and divergence. And vorticity works really well because vorticity is typically a really big number. It's not the difference between two small ones, but it is a big number. So if we can find a relationship between vorticity and divergence, if we can measure vorticity, it'll tell us divergence. So that's why we use the vorticity equation. So what we're going to do in this first video is derive the vorticity equation. We're not going to go through all the guts of it. It's just going to be kind of an overview or an outline of how to do it. And then from there, we're going to go through the vorticity equation and look at each part and describe each part in detail. So the first thing we do is take the horizontal equations of motion. This is why we went through great detail in deriving the horizontal equation of motion, because it's used so much in theoretical meteorology. So the first thing we're going to do is take our x component and our y component of the equation of motion. This is with pressure as the vertical coordinate, meaning that you have a height gradient. That's why you see dz dx and dz dy. You don't see dp dx or dp dy. This is on a constant pressure chart. After that, what we're going to do is we're going to take the left-hand side and expand it. Remember, this equation is a Lagrangian. It's following the parcel. So we have to break down that acceleration term into its local component and then also its advective component. So that's what you see there. You see a lot of derivatives, and those derivatives all are a result of breaking up or expanding the Lagrangian derivative. We can also do that in the y direction. Make sure that what we're doing here is breaking up the left-hand side, the acceleration term, into its Eulerian and advective terms. And then what we're going to do is we're going to do some calculus. We're going to take the derivative of the x direction with respect to y, and the equation of motion in the y direction, we're going to differentiate it with respect to x. In other words, we're cross-differentiating. When we do that, we get a mess, and it is a lot of terms. So we're going to simplify those terms. I'm not going to show them here, but what we do is subtract one from the other, and then start looking for things that look familiar. Like vorticity is the partial or the derivative of v with respect to x minus the derivative of u with respect to y. And we can find divergence in there. We talked about this already, how that's the derivative of u with respect to x and the derivative of v with respect to y. So wherever we see those, we're going to stick that squiggle, that zeta, and also that delta into the equation. And this is what your equation looks like. And it looks like a mess. But we're going to go through each term and explain what each term is. So this is known as the vorticity equation. And the left-hand side, it's the derivative with respect to time of zeta plus f. You probably remember zeta plus f is, of course, the relative vorticity plus the Earth's vorticity, which gives you absolute vorticity. So on the left-hand side, you have the change in absolute vorticity with time. So there are three terms that can result in the change in vorticity with time. And that is divergence, tilting, or friction. Now, the next 2 or 3 videos, we're going to go through each one of these terms and explain what's going on with each one of them. So come back and watch video number 2 on vorticity.